All right, welcome back. Reminder, this is the last talk before lunch, then we'll head out there. Next up is Ben Krasnow. He works at Verily, which is the life science portion of Google or Alphabet, and he's doing advanced prototypes and stuff like that. You can also see him on Applied Science, one of my favorite YouTube channels. He's doing crazy experiments, and I'm sure he'll talk about a bunch of that stuff here. Really good YouTube channel. And please welcome to the stage, Ben Krasnow.
All right, yeah, thanks very much for the intro. It's good to be at the second Hackaday SuperCon. And since the name of the day is Hackaday, I thought we would talk about building sort of things very rapidly and how this can work in sort of a large corporation. So I don't know how many people here have a day job where they work in a large co, but you might have found a little bit of resistance to sort of the Hackaday ethos. And so I'm here to tell you that it's actually a very viable way to be effective in a large organization. And in my talk, I'm going to describe, sort of how it's worked out really well for me, and hopefully some of the same things will work out well for you. So the title of the talk is Building Advanced Scientific Apparatus Quickly and at Low Cost, which if you're pitching your Hackaday ethos to someone, maybe that's a good way to do it if they aren't so on board with the Hackaday lifestyle. But between you and me, I really just like to say build first and ask questions later. It's very effective. It has sort of like the Bayesian model, where you try something, you improve on it, you go back and try it again. You don't have to spend 5 years researching to figure out that it isn't going to work. So in this talk, it would be too dry if I just tried to describe this Hackaday ethos and how it's worked in abstract terms. So I'm going to use a couple examples, and I think we're just going to talk about the first one today, the X-ray backscatter imaging system. And this is a video that I did a while back, but there's actually quite a lot of backstory. So you're going to get to see sort of the behind the scenes of how I built the thing and how this is actually applicable to a real business situation. And so again, if you're pitching this Hackaday ethos to someone who's not fully on board with it, it's good to have points of information that let them know why this is going to be effective, right? So I've singled out three things: crowdsourcing of information and tools, availability of a second-hand market, and easy access to research and patents. And these things have changed really rapidly in the last 10 years or so. So I use eBay quite a lot in my day-to-day work. You can find an immense amount of stuff on eBay. There's also, Alibaba, Banggood, all these things that just didn't exist 10 or 15 years ago. And they actually enable you to do things that you couldn't do before. So we'll talk about that in this talk. And then, bottom line, why does this impact business and research? The reason is that if you can go so much faster than you could go 10 years ago, you can just put things together in ways that have never been done, and you can convince people that this is actually a really good way to do business. You end up making more money this way. So when you're pitching this to the bean counters basically at your company, it is very helpful to describe how this is going to impact the bottom line. A little bit about me. I've always loved hardware hacking. This is a picture of my shop in the San Francisco Bay Area. And I started off as a research assistant at Stanford doing brain research. This is a picture of my brain. That view is called the sagittal view. And while I was there, I realized that the researchers needed lots of tools to interact with people while they were in a brain scanner. So if you're a brain researcher, what you want to do is put someone into an MRI machine and then have them do math equations or reading or exercises, and then scan their brain and look for the functional patterns. So that means you need to have computer peripherals that interact with people while they're getting their head scanned. And that's what I built for my business in 2002 there. Mag Design was plastic joysticks and plastic keyboards that let people interact with computer programs while they're getting their head scanned. Then I went to college, and I would definitely recommend working before going to college. That was a good thing. I co-founded Valve's hardware division. So you heard, hopefully, the talk this morning by Alan, and did quite a lot of work with those guys on virtual reality. And as Chris mentioned, I work at a company called Verily now, which is essentially Google Life Sciences. And so our mission is to build sensor systems that detect disease very early before they can transition into a state that's very painful and very expensive to manage. So rapid prototyping actually plays a big role in this because we want to know what's going to work quickly, and that's really what it's all about. Also, you may know me from Applied Science, which is my YouTube channel. I know the video output has been pretty low these days. I'm sorry about that, but the curing cancer thing has been pretty attractive to me, and so I've spent most of my effort on that. But there will be more videos. It's coming along. I wrote down that I use it as a motivator because if I have to produce a video at least once a month or something, that means I have sort of an effort to put in there, but there will be more coming. Okay, so let's talk about the first example. Who here is familiar with these scanners? This is dating me a little bit because they aren't in airports anymore, just a handful of people. If you flew through in this country around 2011 or so, you probably went through one of these machines. I believe the company is pronounced Rapiscan, but I made the joke one too many times, and so if I pronounce it a different way, you'll have to forgive me. I did a lot of flying in years 2011 and 2012, so I probably went through one of these machines several hundred times and got curious about how they worked and how well they worked and that sort of stuff. And so that's what inspired me to try to build one of these myself. They were all taken out of the airports in 2013 and also banned in the EU because they were too invasive. Obviously, there was a lot of public backlash. But the bottom line is that we weren't sure if they were actually more effective at finding terrorists. The whole point here is that you want to keep people from bringing dangerous stuff onto an airplane. Does it actually work? I mean, who knows? So in this talk, I'm going to describe how you would actually prototype one of these and figure out if it's actually more effective than existing solutions. This was replaced by a millimeter wave. So if you go through the airport and you go through the stance, the machine that has a large wiper that comes around is millimeter wave. The machine that doesn't have the big wiper that comes around is one of these old machines, but you probably won't find them anymore. Build first, ask questions later, and prototype early and often. If you remember only one or two things from this talk, it should be those two phrases. Always build something and test it first, because then you have real data. Prototype early and often so that you have a large pool of solutions to draw from. And that's really this whole Bayesian approach. Like, don't sort of spend forever on one little idea. Try to have a big pool, try different things, and get data from all those different experiments. And that's really the best way to go for prototyping. I should add, none of this really applies to manufacturing. I've had some experience with that, but really most of my experience is in prototyping, and that's really what I'm talking about today. So if you've been involved with manufacturing, there's quite a bit more, methodical planning, plotting involved. This is all about prototyping, figuring out if your idea is actually going to solve the problem that you have to solve. So if you're sitting around, also, this is not a talk about privacy. So I'm not addressing whether these machines are great or whether we should use them or airport security. Try to pretend that you're an engineer at this company, Rapiscan, and you're sitting around with the decision makers, and they're thinking, well, how are we going to catch terrorists more effectively? And so really what you want to know is, if you come up with a new idea, is it actually going to be more effective at preventing terrorists from getting things onto airplanes? So just keep that in mind. This is not a commentary on actual airport security. If you wanted to figure out if this thing is going to be effective or not, these are the kinds of questions that you would ask. Let me see if I can, yeah, that works. Is the radiation dose too much? So again, if you build this system and you find out that it emits 10, orders of magnitude too much radiation to be effective, you can easily, stop working on it and save a whole bunch of time. So it's really all about trying something quickly and measuring and not wasting your time on a solution that won't work. But if you do the experiment and find out that your signal to noise ratio is pretty good, and you've measured the radiation that the person experiences and it's within reasonable limits, then you're okay. So it's really about answering this stuff. How much will the machine cost? You can get a good idea if you have a working prototype of what materials went into it. How good will the resolution be? Again, if you can build a cheap prototype, and you'll see from my video later, you can actually detect small metal objects with parts that you just find on eBay, which shows that it's not really an ultra precision sort of environment. If you can make it work with just cheapo stuff you find on eBay, clearly it sounds pretty viable. And ultimately, is it more effective than a metal detector? If you have a working prototype of this X-ray backscatter detector, just put it head to head with a metal detector and try to get people through them. And so once you answer all these questions, you can very confidently say to the decision makers, well, we've built a new system, we've tested it against metal detectors, it's great. There's no point in modeling or doing sort of hypothetical analysis when you actually have a working prototype. And so the real question here is, why would you use any other development approach? Usually people respond by saying, well, building prototypes is too difficult, it's too expensive, it takes too much money and time. But if you can do it quickly, then why would you use any other technique? So here's my 1-month prototype. From a business planning perspective, having quick answers to these questions is pretty convincing. So in my own work at Verily, I should add, unfortunately, I can't really use an example from my real day job because it's all still secret, of course. So I'm going to use this example from my YouTube channel. This is actually not what I work on during the day, detecting Allen keys in frozen chickens. But that is the demonstration that I used to show that this works. And so this chicken here is wearing a holiday sweater and has a metal Allen key hiding under it. So with this really, pretty cheesy prototype, I only spent a month building it. It's almost entirely eBay and McMaster parts. It's able to detect metal objects that are, of the scale that we're interested in. So how to do it? Having worked in sort of the prototyping industry a little ways, it's common to encounter this slow development, as I call it. And the colors actually mean something. Red means you're waiting on somebody else. Yellow means you're waiting on something, but it's kind of within your control. And green means you're not waiting, you're actually building. And so it's important to get as many green boxes as you can. And that usually means working in a very small team so that you aren't waiting on other people all the time. It's good to have multidisciplinary people that are all sort of ready to work all at once. And as we go through the slides, I'll show you the comparison from slow development to rapid development. And again, this is just sort of formalizing the process. I know I'm preaching to the choir here. This is Hackaday. But my message to you is to go out into the world and try to convince others that this is a super viable approach. In fact, it's the most effective approach for prototyping. Okay, so let's talk about some of the technicals. When I got started, I didn't know a whole lot about X-rays, just basic stuff, and started researching how traditional X-ray machines image things. So most X-rays that you get at the doctor's office are transmissive, where there's an X-ray source shooting on one side of you, the X-rays go through you, some are absorbed more than others, and what you make is a shadowgram on the other side of your body. So where the X-rays are able to penetrate all the way through, you get a lot of signal, and then where they're not able to penetrate through, you don't get very much signal, and that's what creates the black and white images that you see of someone's chest. It's really good. In fact, if you were trying to detect, knives, bombs, whatever, bad stuff getting on an airplane, this is by far the most effective way. The problem is that your flesh absorbs a lot of X-rays. It's not like they all go through and a couple percent get absorbed. It's kind of closer to like 50-50 in some cases, which is a big problem because if you're absorbing all that X-ray radiation, it corrupts your DNA and you get cancer and all that kind of stuff. So even though the TSA, I'm sure, would love to just do transmissive X-rays on everybody that goes through because it's so effective, you'd really just be doing too much damage to all of the air travelers. So, just for comparison, that's basically how this works. I'm sure guys at Rapiscan or whatever thought this would be a good viable approach. Maybe they even rapidly prototyped it and found out that the X-ray dose is just much too high, many, many orders of magnitude too high. We can talk about X-ray tubes. This is actually one piece of technology that hasn't changed much over the last 100 years. We're still making X-rays the same way we did from the very first X-ray tubes. And the idea here is that we get a filament really hot in this vacuum tube, and then we put a really high voltage between the filament and this tungsten target. And what happens is the electrons are boiled off the filament and slam into the tungsten target, and it's the impact that causes the X-rays to come out. It's the breaking radiation. And the reason that they use tungsten is because that happens to produce a very favorable spectrum of X-rays. It's also very temperature resistant, and it's good for a lot of reasons. And you'd think this is sort of a unusual bit of tech, but you can actually buy these on eBay no problem. There's probably 100 of them for sale right now. In higher power models, instead of having a stationary tungsten target, it's actually a rotating disk because the electrons produce a lot of heat when they impact. So what you can do is have your tungsten disk sort of spinning so that the spot of heat moves along the disk and doesn't cook it too much. If you've been through an airport, you've probably seen that they do transmissive X-ray scanning of your baggage. So just because the human body can't take all this X-ray radiation, your baggage is fine with it, and they can get very high-resolution images. What's interesting is that you've probably seen the colors on the screen if you've kind of peeked over the TSA agent's shoulder. Those colors actually mean something. What's happening is the atomic number of the material that's in the X-ray image has a different absorption characteristic for the X-rays going through. And so some of the manufacturers use different colors, but there is a little bit of consistency between them. Here's a backpack, and typically the orange is low Z materials, so basically high up on the periodic table. Water, hydrocarbons, or fabrics. So in this backpack, you can see a couple bottles here of cola, and those are orange. And then green is kind of a mid-Z number halfway down the periodic table. And you can see the camera has some glass in here, which is green. And then blue is sort of a high Z number, so iron, copper, silver, tungsten, all these things. And you can see maybe the camera's case has a denser metal in it. What's interesting is if you want to detect these different kinds of X-rays, it's very difficult to sort of figure out the energy involved in your X-ray. So traditionally how we do this is have two sensors side by side, and you shield one of the sensors better than the other, basically. And the X-rays that are more penetrating will go through the heavily shielded side, and then you look at the ratio to figure out sort of the spectrum of X-rays that have gotten through. So this is all for transmission imaging, but the technology hasn't changed. This is still what we were using in early days. Another interesting problem if you want to make an X-ray imaging system is that we don't actually have a lens material that bends X-rays. You know, we've been making glass lenses for thousands of years even, and glass does a great job of bending light rays. You just have to cut it to the right shape, and then the difference between the refraction in air and the refraction of glass causes you to bend the rays. But we actually don't have a single material on Earth that can do this for X-rays, or even in the universe, maybe. We have diffractive optics for X-rays, but it gets very complicated. We don't have a simple way to make a lens. So in making an X-ray backscatter imaging system, we can't really just sort of take a picture. We can't make such a thing as an X-ray camera. Those shadowgrams that I mentioned at your doctor's office don't really have a lens involved. It really relies on the fact that the X-rays are going through you, and then you have this sort of detector that's very large, and so you're basically making a shadow. Similarly to like the sun shining through trees, you'll actually see little pictures of the holes in the tree leaves on the ground, and it's a shadowgram. There's no lens involved. It's just the effect of the aperture of the sunlight coming through. So to make this backscatter X-ray system, if we can't use a lens because there is no material to make one, we have to come up with a method to send the X-rays out into the world and then collect the return without using any sort of conventional optics. And the way to do that is to scan the X-rays out into the world, kind of like a lighthouse. You know, I kind of say I really like lighthouses. And what you do is you look for the return. It's basically a single pixel camera. So imagine if you had just an optical sensor that could detect how much light is coming back. You could stand in a dark room with a flashlight and just aim the flashlight somewhere in the room and then check your detector, and it would tell you the color or how much light is coming back. And if you wanted to build up the whole image of the room, what you could do is just move the flashlight along and then check your detector each time if it's just a single pixel. So what you do is you build up the image pixel-wise by sending light or X-rays out into the room and then recording how much you get back. And so you don't need a multi-pixel detector or lenses. It's literally just a giant detector, 1 pixel. And the difficulty becomes creating this moving beam. With a flashlight, it's pretty easy because you can just swing it along. And we're going to do something similar for the X-rays. A really good source of information is patents. So Google has a really good patent search tool. There's others out there as well. In this case, a patent already existed for a backscatter imaging system, so I had a huge leg up. If I was developing something that didn't already have a really well-known world product, you'd still find a whole lot of related information. Don't discount the amount of information that is stored in patents. And I make a funny note here, business opportunity, build a site that strips the claims out of patents. So if you talk to patent attorneys, they'll tell you that it's really bad news to cruise through patents because if a competing company found out you did that, it could be triple damages and this and that. And so they generally tell their employees, don't ever look at patents. But what they really mean is don't look at patent claims, because that's where the legal stuff comes in. So I still haven't seen this yet, and I've suggested this a number of times, but someone really should build this, or a site that just goes through patents and just strips out all the general information and doesn't let you see the claims, because then you're safe, right? So I think someone should definitely do that. Oh, sorry. So in this patent diagram, you can see sort of a schematic of the whole system. So we're basically going to shoot X-rays out of our little pixel creating machine, our lighthouse basically. And then we're going to have a really big detector because the signal that we're getting back from the scene is not going to be that great. We need a large area to collect all these X-rays. And so here's my version of this detector. As you can see in the diagram here, it looks like a big box. And in the text, it describes it pretty well. And I built a copy of it. And here's my copy. It's basically a giant phosphorescent screen that they would use in old-fashioned doctor's offices. And they would actually load film into this thing and then put you in front of the X-ray machine, and the light from the phosphor screen would expose the film. They'd take the film out of the cartridge, develop it, and that's where the classic chest X-ray films came from. Again, you can find these on eBay. I mean, there's just so many laying around from doctors' offices that have been decommissioned that these things are dirt cheap. I mean, we're talking like 10, 20 bucks. You can get as much phosphorescent screen as you want. So what I did is I put it inside a black coroplast pyramid and lined the inside with aluminum foil. And that's basically my photo collector. And then the actual detection mechanism is a photomultiplier tube, which is just a very sensitive light detector. So the light that's generated from the phosphorescent screen in there is detected, converted to an electrical signal, and that's how we're going to get our signal out of this whole system. If you're interested in phosphors, there's actually a lot of interesting stuff there too. Since we're scanning this system along pixel by pixel, we want a phosphor that's really quick. So if we're scanning along and suddenly we go from like a bright pixel to a dark pixel, we want our phosphor screen to transition from lots of light to no light really quick. And if we want to build up an image really fast, we have to scan through all those pixels in the scene very quickly. So we want to pick a phosphor that gives us a lot of light but is also really quick. And if you're interested in jumping down a rabbit hole, that is a deep one, since there's lots and lots of phosphor science out there. But luckily, in the patent, they did say which one you should use, so I knew exactly which one I needed. Here's a 3D model of the device that I built. In the middle here is the X-ray tube, and the way that I'm going to cut the beam up is to basically have a steel plate with a hole in it that rotates past the beam. It's the lighthouse again, for sure. Lighthouse with X-rays. And in the vertical direction, I'm just going to tilt the whole apparatus. You'll see this in the video later, but the whole thing will tilt. So I have basically a pencil beam that scans across, just like the raster pattern in an old CRT television, just back and forth, top to bottom. So here's our shopping list. We got an X-ray source, a phosphor screen, a light-tight housing for the detector there, a photomultiplier, some metal parts, and a way to integrate all this. And we want to answer the question of whether this thing is going to work. So here's a comparison from sort of the slow method that I mentioned to the rapid method. If you're a slow method, you would say, okay, let's talk to an X-ray expert and get some of this equipment in here so we can test if it's going to work. And I'm sure, how many people in here have had the conversation with sales reps that start off, well, how many units a month are you going to order? And you say, I don't know, I'm prototyping. They say, well, okay, then we're going to have to bring in someone else. We need some more application details. You're going to have to set up a meeting, but the guy's out of town, so then it's 2 weeks later and this and that. Anyway, it's going to take hours or days of searching and emailing, and it's not going to be less than thousands of dollars. Whereas you can just do 20 minutes of searching on eBay, 4 days of shipping, under a few $100s, and you've got the part. And again, this is not to say that manufacturing is so easy. We literally just want to build this thing quickly so we can see if it's going to work. Just use eBay. The range of stuff that eBay has is just astounding. So I found a story where these guys were doing security research to figure out if backscatter detectors were, in fact, more effective than metal detectors. This team at UC San Diego wanted to test it, just like I've been saying. So where do you think they found a scanner to try it out? You can buy the whole Rapiscan already done on eBay for $9,000. So no matter what field of research or hardware development or software development you're in, you can find something on eBay that will make your job easier. I don't work for eBay either, by the way. Okay, so then we're the X-ray detector I mentioned. Where do you find this piece of phosphor film? It's not easy. I mean, you can't go to McMaster or DigiKey or something and get it. But again, eBay has it. It takes 10 minutes, 23 bucks. Done. Photomultiplier, similar story. You could buy it from an off-the-shelf vendor. You save a little bit of money, but that one's kind of about the same. To integrate the image, again, this is super hacky. It's really quick just to get an image going as quickly as possible. I just used a potentiometer plugged into the y-axis, which I'm going to tilt up and down with my hand because I didn't have enough time to do a motor and figured out that I could make an image even without motor control over the y-axis. In the x-axis, I've got this spinning disk, which is not rotationally controlled. It's just open-loop motor. And I've got an optical reflectivity sensor, again, very similar to the lighthouse. It's kind of funny these two talks happened on the same day since there's a number of similarities. And to make the image, a lot of people would say, oh, if you want to collect an image, you should probably use, an FPGA or microcontroller, collect the data, integrate it, and put it into a thing. But again, we want to go much faster than that. Instead of spending days or a week putting that together, I just used an analog oscilloscope. And the image is going to appear on the screen. And the way that I'm going to integrate it is just by putting a camera on the screen with a really long shutter and open the shutter, and the image will present itself on the oscilloscope screen, and that's how I'm going to get my data. So let's take a look at a video of this thing in action. Turn to your left, hold your hands above your head, hold still for 10 seconds. Thank you. Just as I suspected, trying to sneak an Allen key through. So, it's pretty silly. Hey, everyone. There you go. I've been working on this project for a while. This is a X-ray backscatter imaging system, very popular in airports these days. And this works on the principle that if you shoot X-rays at something, some of the X-rays will penetrate through the object, some will be absorbed, and some will be backscattered or reflected off. And if you catch the backscattered reflection, you can make an imaging device like this, just like is used in airports. One of the problems with imaging things with X-rays is that we don't have the equivalent of a lens for X-rays. So for a standard light-based camera, we can just use a piece of glass to make a lens. I think the time would be better spent with questions anyway, so I would like to hear from you. And remember, build often, build first and ask questions later is really the best way to go. And this technique shows it. It's viable in business. I know I didn't spend quite as much time on that, but just stay tuned to Verily, and you'll probably see some of my stuff coming out hopefully next year. Thanks very much.